For 5,000 years, humanity has been waging a silent war against gravity and the world's most terrifying voids. Every river was a border. Every valley was a prison. Every strait was a curse. But we never surrendered.
The cable
From
tension
fragile
pulls
stone
upward
slabs
and
to
inward
massive
at
steel
every point.
arteries defying
It
nature
is
itself,
tension, not compression.
we transformed deadly gaps into the backbone of global trade. In this documentary, we'll witness 5 revolutions across 5,000 years. From the weight of stone to the elegance of steel, from brute labor to computer simulation.
The vertical
Every
hanger
bridge
cables
built over an
transfer the
abyss
massive
represents the
load of
moment
deck
a civilization
below
erased the word
distributing the weight
impossible
along the
from its
main cable.
vocabulary. Get ready to discover the engineering breakthroughs that finally conquered the impossible. What actually stops a 100,000-ton bridge from plunging into the void below? Yet the answer isn't concrete. It isn't steel. It isn't cables. The answer is the invisible laws of physics. We'll unravel the secrets of bridge engineering by decoding the hidden mechanics of arches, beams, and tensioned steel. From Romans weaving ropes out of stone, to modern engineers taming the wind with mathematical equations. Witness 5,000 years in the evolution of structural genius. The genius that transformed primitive crossings into humanity's most enduring wonders. Ancient civilizations faced a deadly choice. Find a way across or remain forever divided by the world's great separations. Rivers split empires in two. Valleys shut down trade routes. Straits severed continents from one another. This documentary is the story of how primitive builders, through radical innovation, conquered impossible heights and became master engineers. A journey that began with a single tree trunk now continues with steel wings soaring 300 meters above the ground. Follow the 5,000-year timeline of the structures that reshaped our planet and wove our world together like a net. Every arch is an equation, every cable is a prophecy, and every bridge is the greatest gift physics ever gave to mankind. 5,000 years ago, the first bridge was a fallen tree trunk. An oak or a plane tree toppled into a river by a storm. An accident. But from that accident, an idea was born. If nature could lay a tree across a river, we could do it deliberately. Humanity had made its first engineering decision. The earliest bridges were built from raw materials with raw force. Stone slabs, logs laid side by side, ropes stretched between two rocks. These weren't calculations, they were instinct. The concept of mathematical load distribution hadn't been invented yet. Ancient bridges knew only one strategy for fighting gravity: raw mass. Thicker stone, more supports, heavier foundations. If the bridge collapses, build a bigger one. This strategy worked, but it had a limit. Stone is heavy and cannot span large gaps. Any stone beam longer than 10 meters collapses under its own weight. The revolution came from Rome. The Romans perfected the arch. The arch is one of the most elegant inventions in the history of engineering. Its principle is profoundly simple, but its effect is revolutionary. It converts a vertical load into lateral compression by pressing the stones against one another. Every voussoir leans on the stones beside it. Pull the keystone at the top and the whole structure collapses, but leave it in place and every stone locks the others. The force of compression holds the structure upright. When the Romans applied this principle to river bridges, waterways that had once seemed impassable became crossable. The Ponte Fabricio was built in 62 BC and still stands in Rome today. A bridge that has served pedestrian traffic for over 2,000 years. The Romans didn't just build bridges. They laid the circulatory system of an empire. Every river crossing was a trade route. Every trade route was a military corridor. Every corridor was the empire's expansion. Bridges were Rome's instrument of conquest. The transition from raw natural materials to early stone masonry represents the first great leap in the history of engineering. Temporary crossings became the permanent monuments of an empire. Stone was no longer just weight, it was calculated power. The arch was no longer just a shape. It was the first formula ever written against gravity. The power of the triangle and the railway age, 1700 to 1900. In the late 18th century, the world began to change. The Industrial Revolution created an unprecedented demand for connectivity between factories, mines, and cities. But the real revolution came with the railroad. Locomotives weren't just carrying people and goods. The loads they carried had long since exceeded the capacity of traditional bridges. A Roman arch could support a legion of soldiers, but it couldn't handle the dynamic load, vibration, and repeated impact of a 100-ton steam locomotive. Engineering discovered a new structural unit: the triangle. The triangle is geometry's most rigid shape. Push a square and it becomes a parallelogram and collapses. But push a triangle and it holds its shape. This simple geometric truth transformed bridge engineering at its roots. The truss bridge was born. In truss systems, metal rods are joined in triangular arrangements.
And every foundation
Each triangle
holds.
distributes forces to neighboring triangles. The result: you can carry far heavier loads with far lighter materials. Cast iron, and later steel, became the material of this triangular revolution. In England, America, and every corner of Europe, railway bridges rose. The fourth bridge in Scotland was constructed between 1882 and 1890. Its span, 521 meters. At the time of completion, it was the longest bridge in the world. 54,000 tons of steel were used. The fourth was the triumph of the truss system. But it also symbolized a transformation. Bridge engineering was no longer an intuitive craft. It was a calculated science. Engineers were no longer saying this looks strong enough. They were calculating material strength, mapping load distribution, and determining safety factors. This transition was critical. The shift from intuitive approach to precise physical principles laid the groundwork for the age of iron and steel. The triangle gave engineers a language, and with that language they could fight gravity, not with raw mass, but with geometry. Less material, more resilience, longer spans. The triumph of the triangle opened the door to the revolutions of the 20th century. Suspension bridges and the steel cable revolution, 1870 to 1950. In the late 19th century, engineers came face to face with a limit. Truss bridges were powerful, but beyond a certain point they became inefficient under their own weight. In spans exceeding 500 meters, the steel truss structure grew so heavy that most of what it was carrying was itself. A different approach was needed. The answer came from above: the suspension bridge. The principle was ancient, but the application was revolutionary. Instead of supporting the deck from below, suspend it from above. Main cables anchored to massive towers trace a parabolic curve. Vertical hangers dropping from those cables hold the deck in the air. The deck no longer has to carry its own load. The cables carry it. The cables transfer it to the towers. The towers deliver it to the foundations. The Brooklyn Bridge was the manifesto of this revolution. Completed in 1883. Span: 486 meters. At the time of completion, it was the longest suspension bridge in the world. Its engineer, John Augustus Roebling, perfected steel cable technology. Each main cable was woven from 5,754 individual steel wires. Each wire was pulled, laid, and compressed separately. This process took 14 months. Brooklyn was not just a bridge. It was proof of suspension bridge physics. When rigid beams gave way to flexible cables, spans could multiply. But every revolution has a cost. In 1940, the Tacoma Narrows bridge disaster struck. This suspension bridge in Washington state was vulnerable to wind because of its lightened deck. Winds of 65 kilometers per hour drove the bridge into resonance. The deck began to undulate. The wave amplitude grew. The structure entered aeroelastic flutter and tore itself apart. The disaster was captured on film and became the most famous failure footage in engineering history. Tacoma delivered a lesson. A bridge must resist not only weight, but wind. Aerodynamics became an inseparable part of bridge design. Wind tunnel testing became standard. Deck cross-sections were reshaped into aerodynamic profiles. The legacy of catastrophe was safety. When the Golden Gate Bridge was completed in 1937, its span of 1,280 meters made it the longest suspension bridge in the world. Its Art Deco towers, international orange color, Darren's silhouette rising through the San Francisco fog, made it not just an engineering achievement but a cultural icon. The Golden Gate proved both the power and the beauty of the suspension bridge. Gravity had ceased to be an enemy. It had become a partner. Weight was entrusted to cables. and the cables carried it with grace. Engineering and aesthetics had achieved their most perfect harmony. From Millau to mega bridges, 1950 to 2020. In the second half of the 20th century, bridge engineering shifted to a new paradigm: cable-stayed bridges. In suspension bridges, cables trace a parabolic curve and carry the deck via vertical hangers. In cable-stayed bridges, cables run directly from the tower to the deck. Straight lines, geometric clarity. Each cable is a force vector, and the engineer can calculate every vector individually. This design brought one major advantage: modular construction. The deck can be built section by section. As each section is set in place, cables are attached and it begins carrying load. No scaffolding required. You don't need to close off the river or valley below. In midair, piece by piece, the bridge builds itself. The Millau Viaduct is the masterpiece of this technology. It soars over the Tarn Valley in southern France. Its highest point, 343 meters, taller than the Eiffel Tower. Total length, 2,460 meters. 7 massive pylons carry the deck, and from each pylon, fan-shaped cable stays reach down to the roadway. Upon completion, it was the tallest bridge in the world. Architect Norman Foster and engineer Michel Virlogeau collaborated on the design. The result was not only functional, it was breathtaking. Millau proved that a bridge could be a work of art. Another defining force of this era was the computer. Finite element analysis software allowed engineers to calculate thousands of stress points in real time. Slender deck profiles, elegant tower geometries, and spans previously considered impossible could now be simulated and built. The computer gave engineers a third eye. They could now see the forces, stresses, vibrations, and wind effects at every point in the structure, before construction even began. The Hong Kong-Zhuhai-Macau Bridge represents the global trade dimension of this era. 55 kilometers long, a mega infrastructure of sea-crossing bridges, artificial islands, and underwater tunnels. It connects 3 cities. Construction took 9 years. These bridges no longer just connect 2 shores. They connect economies. They bring continents closer. They form the physical backbone of global trade. In the 21st century, the bridge became a phenomenon beyond engineering, a symbol of a nation's technological capacity, economic power, and international connectivity. Cable-stayed systems wrote the structural language of that symbol: smart bridges and mega projects, 2020 to future. As the third decade of the 21st century opens, bridge engineering has reached a new threshold. The question is no longer, how long a span can we cross? The question has become, how smart can we make the bridge? The new generation of mega bridges completed around 2026 can diagnose themselves. Carbon fiber reinforced concrete is 5 times lighter than traditional steel and completely corrosion resistant. But the real revolution isn't in the material. It's in the nervous system inside the material. Fiber optic sensors are embedded directly into the concrete and steel structure. Temperature, stress, vibration, and deflection are measured at every centimeter. Data streams to the cloud. Machine learning algorithms predict structural fatigue weeks before a crack forms, while maintenance alerts are automatic. Repair plans are prepared in advance. The bridge is no longer a passive structure. It is a living organism monitoring its own health. The most ambitious projects of the future aim to connect continents. The Bering Strait Bridge concept, 85 kilometers between Alaska and Siberia. If built, it establishes a road connection between North America and Asia. The Strait of Gibraltar Bridge, 14 kilometers between Spain and Morocco. It unites Europe and Africa. The Strait of Messina Bridge, a 3,300-meter span between the Italian mainland and Sicily. When completed, it will be the world's longest single-span suspension bridge. These Great Division projects represent humanity's confrontation with its last geographic barriers. Each one is technically feasible. Each one is waiting for political and economic will. But perhaps the most exciting innovation is also the quietest: energy harvesting bridges. New designs integrate wind turbines into bridge towers. Solar panels are installed on the deck surface. Piezoelectric materials generate electricity from traffic vibrations. The bridge no longer just consumes energy, it produces it. It powers its own lighting, sensor network, and traffic management system with electricity it generates itself. Carbon footprint approaches zero. 5,000 years ago, when we pushed a tree trunk across a river, we only wanted to get to the other side. Today, bridges connect continents, generate energy, and monitor their own health. But at the core of every bridge, the same idea remains: to connect the two sides of a void. For 5,000 years, every engineer, every worker, every stone faced the same question. How do we cross? The answer changed every time. Stone, iron, steel, cable, carbon, digital. But the question never changed,
Two
and it
distinct
never will.
philosophies of bridge engineering.
Because as long as
Standing
humanity
side by
exists,
side
there
with
will
one
always be
common
one more
goal.
void to cross.